Okay, and just in case you didn't get it enough, we are changing our schedule, so I just wanted to make sure you're aware of that. Again, we're going to go through, finish up chapter 5, I think, in this lecture, and then we will shift to the alcohol chapter on Wednesday. We'll go through a lot of the alcohol reactivity, then probably do a little bit of amines, and then we'll have exam 3 at our regularly scheduled date. So, let's go ahead and get chapter 5 finished off. So we've got our homework. Excuse me. We're primarily looking at reactions now. So be aware of that. You're going to see mechanisms applying how alkene functional groups react with different reagents. So we're looking at, I think it's roughly 6 or 7 new chemicals that can be used in individual reactions. You're going to have to be cognizant of how they react with double bonds, where different atoms go, that kind of fun stuff. And believe it or not, stereochemistry as well is going to rear its head. So, we talked about this already. Alkenes end up being more reactive than the alkanes because of that pi bond, that extra p orbital. So if we looked at it from the side, we rotated it upwards. We've got our hydrogens going away and towards, and to get that pi, or that double bond, that pi bond, we've got these p orbitals. Okay, so it's these p orbitals out here where the electrons are forming that double bond that end up giving us the reactivity. Okay, so it's those electrons that we need to be concerned about, and it's the geometry of this overall shape, terribly drawn, that's really going to determine stereochemistry and ultimately how different double bonds react. Okay, because it does end up being a source of electrons. We're looking at alkanes or alkenes acting as your any type of base, be it Bronsted base. You can see it as a Lewis base and sometimes as a nucleophile. It tends to be a lot more rare, just because the electron density is shared between atoms, not specifically on an atom. So the primary reactivity that we're going to see with our alkenes is really going to be kind of that Bronsted base chemistry. And to get it to act as a Lewis base or a nucleophile, we have to level up the reactivity, make sure the reagent that we're working with is electrophilic enough to allow for the reaction to occur. Okay. We did look at a generic reaction, so instead of looking at that, the first thing we can do is say, okay, let's take a look at an alkene or a double bond. Whoa, I didn't want to do that. Wanted that space in the middle, so what we can do is draw out an example alkene. So if we've got an alkene, it's just carbons. At this point I'm just going to focus with carbon-carbon double bond. And if we're going to draw resonance structures, there's 2 possible ways that we could do this. We could move the electrons from our pi bond onto, say, the leftmost carbon. And if we did that, we aren't changing the sigma structure in between, but we are moving the pi electrons. So we're taking those 2 electrons and we're sitting them on that carbon. That makes that carbon negatively charged. What happened to the other carbon? Lost an electron, ends up being positively charged. Excuse me. The other option for resonance, I guess I should fix my arrows here, is if we took our electrons and we moved them the other direction. We end up with a different resonance, quote-unquote different resonance structure. In this case, the electrons are now on our rightmost carbon, negatively charged, and our other carbon, if it actually draws, there we go, is positively charged. When we look at these 2 versions of resonance, we don't see a difference between them, and that's because ultimately there isn't. We haven't specified what those other carbons are attached to, which means both of these are valid, which means if we're going to react the alkene, we would expect both of these possibilities. So that if we were going to go through and run a reaction further after this and add some reagent, let's just call it R for the moment, we would end up with 2 products. So if we take the alkene and we just add reagent R, we get two products because there's two possible resonance structures that are valid within this. What happens if we change the structure now? So let's go through and say our rightmost carbon has another carbon attached to it. Okay, so if we go down to our resonance structures and now add that extra carbon. Okay, so now when we go through and look at this, these structures are different because in the leftmost we have the negative charge on a carbon that's only connected to one carbon. If we look at the rightmost, our blue one, that negative charge is on a carbon that's connected to two carbons. So we're changing our resonance structures, and because there's now a difference between them, we would then have to evaluate, is one a more likely contributor or a higher percentage contributor than the other, in which case that's the one that's going to lead to products. Okay? So this is why we look back at our cation and potentially anion stability as well. So if we go through and make the cation argument, okay, so let's go through and say, let's do this argument in green. So if we take a look at our cations, we know something about stability of our cations from, what did we do that in? Chapter 7, I think. So our tertiary cation, secondary, primary, and zeroary. Our tertiary is the most stable. Okay, why was it the most stable? The carbons have more electrons than hydrogen to be able to stabilize that carbocation. Okay, so the increased electron density around the positive charge stabilizes it, makes that cation better. Okay, if we go back and look at our resonance structures that we've got drawn in the middle, if we go through and take a look at our carbocation, what kind of carbocation do we have in the red? Well, we've got a secondary carbocation. Not the greatest, but that's kind of irrelevant at this point. All we're trying to do is see which of these resonance structures is better, not necessarily the best. Okay? If we now look at the blue one, what kind of carbocation do we have? Well, and again, yes, we're going to have to assume that we don't have those extra bonds out there. I know those carbons aren't technically satisfied, but let's just assume that whatever's not shown is to hydrogens. Okay, so that carbon would then be primary. Well, which carbocation is more stable, our secondary or our primary? According to our rules, secondary should be more stable, which means if I'm going to look at the reactivity of this alkene, I would expect the leftmost carbon to be the most negative and that middle carbon to be the most positive, so that when I go through and now react this with some reagent, I can find positives and negatives within that reagent and match them up. Okay, so that's kind of the idea behind this. Let's attempt this argument again, except this time, instead of looking at the cation, let's see if I can step back through this, let's look at the anion for reactivity. Okay, so let's keep clicking out of this, and let's pretend we now look at the anion, so the negatively charged carbon. So as you may or may not remember from chapter 7 again, between these we still have a zeroary, primary, secondary, and tertiary. Which of those ends up being the most stable? Our zeroary is the most stable because, okay, we're looking at the negative charge being the most reactive thing there. To minimize its reactivity, I want to get the electrons as far away from it as possible. So again, when we compare hydrogen, say, to a carbon, carbon has more electrons. In the case of the tertiary, we're pumping a lot of electrons in the same area. Generally a bad thing to do, so we would look at our zeroary being the most stable, okay, and our tertiary being the least. So again, let's go back to our structures, our two resonance contributors for this structure. And we say, okay, that anion is what? Okay, well, it's only got one carbon attached to it, so it's a primary anion. If we look at our blue structure, it's a secondary anion. Which was more stable, primary or secondary anions? The primary, which means, again, our leftmost structure ends up being our reactive species, the one that we would predict for higher product formations. Okay, so understanding the stability between our anions and cations comes in really, really important when we're looking at the reactivity for alkenes, as well as our alkanes or our alkyl halides and substitutions. Okay, so you absolutely must remember this. If it's something that you don't think you can memorize, the next exam and with the final as well, I will allow again a cheat sheet. So get this put on the cheat sheet right away. You know you got to know it. Stick with it. Make sure you're constantly going back and referring to it. Okay. So let's take a look at another example. So what we went through and derived was this rule of where the alkene reacts and how it reacts. Oops, I shouldn't have shown that initial structure. We'll come back to that. So someone actually went through and came up with a rule for this, and this is where you get Markovnikov's rule. Okay, and his rule was ultimately the rich get richer. So we're going to add hydrogens to our double bond where there's already more hydrogens. So when we go through and take a look at the double bond in this structure, man, I really didn't get enough of this. If we've got our double bond right in the middle there, so we can highlight those two carbons, it's those two carbons that are ultimately going to be reactive because it's the pi electrons shared between them that are shuttling back and forth. So between those two positions, we need to decide where should I put the hydrogen, where should I put the chloride. Okay, deciding which one to do first, we'll come back to in a second here. So we need to decide where to put those. If we take a look, let's go ahead and use different colors here. If we take a look at the red carbon, oops. So now we can take a look at the red carbon. How many hydrogens are attached to that carbon? Well, if you go through and look at the bonds, how many bonds do we have? Got 1 bond, 2 bonds, 3, and 4 bonds. Carbon's supposed to have 4 bonds, so we're done. Can we add any hydrogen, or are any hydrogens implied? No, so we're looking at 0 hydrogens on the red carbon. That doesn't look very nice, does it? Let's try that again. Let's say 0 with a slash. There we go. 0 hydrogens on our red carbon. If we go through and take a look at our green carbon, how many bonds do we see there? Well, 1, 2, 3 bonds shown, which means we have to have a 4th implied hydrogen. Okay, what does that mean for us? Well, that means there is 1 hydrogen on that carbon. So if we're going to go through and try and predict our product, so for the moment, ignore that middle structure. If we're going to try and predict what our product should end up looking like, we wouldn't expect anything to change to the ring, okay, or to any of those carbons. But now we would predict to put our hydrogen, okay, at our green position, okay, because that carbon already had a hydrogen. So we would add our acid hydrogen there. Okay, and again, I'm going to try and color code, so bear with me here. We would add our hydrogen there as our new position. The other atom, because we're trying to do an addition reaction, we're going to have to account for where that chlorine goes. That chlorine is going to have to go to the other reactive position. Remember, at this point with this structure, we only have 2 reactive positions. So HCl giving us 2 reactive species, we would predict the HCl to go to the other reactive position, or our chloride to go to the other reactive position. And there we go. Okay, and we've got our final product without looking at a mechanism. Okay, so this rule can be helpful, particularly with predict the product type reaction. So the last series of questions that you got on the last exam. Tell me what the product is. Tell me what the reagent is. Identifying those pieces you can just start shuttling those things in without actually applying the mechanism. Okay, putting it together. Okay. The other thing that we could go through and do now is evaluate again the mechanism. So let's go through and do that, because again we're concerned about looking at all the different ways to do this, and repeating is going to be helpful. We could go through and say which is the most reactive species, HCl base test. You're pretty sure you don't want HCl in your face, so let's go ahead and say that's the most reactive one. We're looking at very large partial positives and negatives on that hydrogen and chloride, which means we need to find partial positive and negative and charges within the other starting material. This is where we can go through and evaluate the resonance contributors for this. I didn't leave a whole lot of space for this, but for that top one, okay, we can say we've got the resonance contributor where we put the positive charge on that carbon. Hopefully it'll look a little bit better when we do it for the other structure. So we've got one resonance contributor where what I've done was shift the electrons like so. The other option, let's go ahead and do it in orange, okay, would be where I put the negative charge on the other carbon. So the negative there and the positive here. Okay, so mechanistically what I did was took the electrons in the pi bond and I put them on that carbon. Okay, so now what we could do is evaluate these two resonance contributors. Okay, which one is the best? So again, it's ultimately your decision. Which do you think is more reactive, the positive or the negative? I personally jump on the positive, so because I'm such an optimistic person, right? Hopefully you weren't laughing too hard at that. Let's take a look at our orange resonance contributor. We've got a secondary carbocation. And with our black resonance contributor, we've got a tertiary carbocation. Okay, which is more stable, tertiary or secondary? Tertiary, which means we would expect the tertiary cation or the tertiary reactivity to propagate through to a final product, which means we would not expect to see anything in the secondary. That doesn't mean it doesn't happen, but it doesn't happen in a high enough amount to make it worth considering. Okay? We will see a lot more of this kind of iffy chemistry when we move into carbonyl chemistry. At this point, we're pretty much talking in absolutes. When we look at the reactivity of this alkene, we only see that tertiary carbocation product. Okay? We won't see the secondary one, okay, as far as we're concerned. So once I've got that reactivity, I could go through and draw resonance, or not resonance, a mechanism starting from my resonance structure. Okay, I could do something along those lines. Ultimately up to you. In general, what we would start with instead is use the resonance ultimately as a teaching lesson to guide you into understanding where it's coming from. When it comes to a mechanism, we would say it's the pi bond reacting with that hydrogen. Okay. Remember, arrows show the flow of electrons. We're making or breaking bonds with these. So in this case, we're taking electrons from a bond and sharing them with an atom. We're making a bond. So hydrogen now has two bonds, which is too many. So we have to break a bond. We can either break the bond we just made, or we can break the other bond. Okay, so we'll move those electrons onto the chloride. This gives us our chloride ion with the electrons that were originally in that hydrogen-chlorine bond. And because we said our tertiary cation was more stable, the hydrogen's going to go to our secondary position, or the position that already had more hydrogens. Okay? This gives us our carbocation intermediate. From the carbocation intermediate, it's still reactive because of that positive charge. So we can now have the chloride share its electrons with that carbocation to form the product. Okay? And what we end up with is our final product. Okay? So we've seen now several ways to go through and approach this. I'm going to tell you right now it's going to get a lot more difficult as we move. So if you've got questions, write them down now so that when we come into class on Monday, you can fire off questions while you're practicing quiz questions. Okay? So let's go ahead and tap this up because we're going to add some complexity to this. So there's everything broken down. I've got one more thing to pop up on this. Stereochemistry issues. And so while you're thinking about that, let me go back through and add the resonance arrows, or not resonance, the mechanism arrows again. So we can see those. We get our product. So we get three mechanistic curved arrows to show the formation of our product. You'll also notice that I don't show the hydrogens in the final product. Why not? Organic simplifications, we're allowed to ignore those, okay, or imply them. So you will typically not see them drawn on. If you're asked to provide a mechanism, I will give you the reactant and the product. You probably will not see the hydrogens in the product, which means you need to be responsible for adding those hydrogens to it if it's something that you don't or haven't already started to internalize. Okay. So now let's shift to that question shown at the bottom there. Stereochemistry issues. Well, as soon as you hear stereochemistry, what you should be thinking would be chiral carbons, which as far as we're concerned for this course means a carbon with 4 different things attached. Okay, so let's go through and take a look at our product. Okay, do we have a carbon with 4 different things attached? Okay, usually a good idea to address where the reaction occurred. So we'd be evaluating either this carbon or this carbon. Okay, I need to make sure I'm using different colors so we can talk about it a little bit better. The green carbon has 2 hydrogens attached to it, so that's not 4 different things. So we can ignore that one. So let's go ahead and erase that. How about the red one? Well, the red one, we've got the chlorine. So if we were already going to try and jump ahead and determine what kind of product we had here, we could say that's a 1 priority. We've then got carbon, carbon, and carbon coming out from that. Well, I don't really see a difference there, so we'd move on. We could go out to hydrogens, okay, for all of these. Sorry, that one was a bit messy. Still no difference, so we go out for a little bit further. Carbon, carbon versus hydrogen. We've now found our lowest priority, being that methyl group off the top. That ends up being our 4 priority. Then we run into a dilemma between the other 2 carbons, okay, trying to decide between the next 2, because if we go back out, hydrogen, 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 so we go out to the next atom and we end up at the exact same spot. So can that carbon be different from itself? No, which ultimately means no stereochemistry. Okay. Is it possible that we could have changed this problem so that stereochemistry did show up? Okay, and we can do that relatively easily. So what I'm going to go through and do is change the structure, since 4 and 1 will end up being the same in either situation. I'm going to go back to the starting material, and now I'm going to add a methyl group here. Okay, and just to make sure we're extra clear on that, let's go through and actually specify these, the CH3s. We'll do that with our top one as well. So when we move through to the product, I've got that 4 in the way. It's a bit irritating. We'll just have to imply that. CH3, CH3, which is again a 4. Okay, so now when we go through and we compare those 2 carbons, again, no difference, so we move to the next position, carbon versus carbon. What do we end up finding? This carbon is a higher priority. Our box is higher priority than our triangle, which means this carbon is higher priority than this, which means that is a stereocenter. Okay, why is that a problem? Well, if I have a stereocenter, when the chlorine reacts, I need to make sure I specify the stereochemistry about that stereocenter, okay? Because I could get multiple products, both R and S. Okay, so I need to be aware of how the reaction occurred. Okay, so this is where you would absolutely need to know the mechanism. Okay, so we go back to our starting material. Do we have a stereocenter in our starting material? No. Okay, do we have a stereocenter in our intermediate? No. So what does that mean about our product? Okay, we didn't have stereocenters to start with. So when we get to our product and we have a stereocenter, this is where it gets a bit tricky. What does that mean? Okay, what should the configuration be about that stereocenter? Okay, about, let's go ahead and star that green. Do we have R or S? Bit of a trick question. We have both. Okay, if you were asked to specify this product, you would have to say, green's always a good color, you would have to say this was a racemic product. Okay, or if you specified the wedge in there, you could say plus enantiomer. Okay, as I saw in another class by another professor, the other option is you could say plus minus. Okay, again, ultimately all referring to the same thing. This is a racemic product. That chloride can either be wedged coming at you or dashed going away. Why? Well, go back to the intermediate. Okay, that reactive carbon, okay, it has a positive charge. What's the hybridization of a carbocation? sp2, which means that positive charge is sitting in an empty p orbital. An empty p orbital, in the case of this drawing, is coming out of the plane and going away from you. That chloride can either come in from the top and be wedged in the product, or come in from the bottom and be dashed going away. Which means two possible products. Since we haven't specified how the chloride can favor one over the other, and we won't go through any kind of trickiness like that, we would end up saying that we form both products. Okay? This is something that's going to be relatively consistent for all of the alkene addition reactions. You end up with racemic products. You get two products. Okay? This is something that you should specify in your answers. If you don't specify that, I have to assume you just kind of guessed at it. Okay? You get partial credit because you've shown where the correct place for the hydrogen in the chlorine, but you don't specify that you understand the mechanism of it. Okay? Hopefully that makes sense. I know, it's a bit to get through. Okay? So let's go ahead and move on, which I think is moving on to problems. So I'm going to give you roughly a 5-second pause here where I won't say anything. Please pause the video and try and work a few of these on your own. Some of these will show up on your quiz. Some of them are going to be a little bit more challenging than others. Identify what things changed, particularly for the last three. Whoops. Don't look at the next answers. Particularly for those last three, try and identify what things changed. Okay. So for the first ones, I want products. So we'll call it P for products. For that third one, I want a reactant. For the top one, I want a product. And then I want a reactant or reagents, which would typically get shown drawn over the arrow. But if you're drawing this out with your notes, you can always do a plus and then show the arrow. Okay. So with these last three reactant ones, try and identify what things changed. The reactant has to account for whatever that change was. I will tell you right now that those changes, for at least one of them, actually most of them, you don't know. Okay, so those last three are a bit of a challenge. So here we go. I said 5 seconds probably 10 minutes ago, so let's go ahead and do our 5-second countdown. 5, 4, 3, 2, 1. Okay, So hopefully you've already paused it and you've worked these so you're familiar with the answers. I'm not going to talk too much about them, we'll just kind of go through them. That first reaction, we're looking at an addition reaction. When we go through and look at it, we're going to add our hydrogen and our chlorine. We're going to put the hydrogen at our most substitute, at the position that already has the most hydrogens, which would now be that red carbon. Okay, because I can imply hydrogens, I'm not even going to show that extra hydrogen, and the chlorine would go to the other position. Okay, so the two reactive sites in that structure are now highlighted in red in the reactants, and they're also showing up now in red in the products. Okay, do we have a stereocenter? Okay, you should be able to say no. If we go back and look at green, these two CH3s are identical, no stereocenter, so we don't have to worry about that. Okay, if we look at the next one, hopefully I'll get tricky on this. Be good with my guessing. If we draw this out, we get our basic sigma structure again. Can go through and highlight in red our reactive positions. Okay, and we would put the hydrogen at the position that already has the most hydrogens. So let's go ahead and say it's the lower one, which means we can put the bromine there. In theory, you got a different answer. Hopefully you did. Okay, and I'm not saying hopefully because the answer I just drew here was wrong. It's actually right, but it's only half right. Okay, hopefully what you provided for your answers was two products. Why two products? Which of those red carbons to begin with has the most hydrogens? Okay, so we go back and look at these two. They both have the same amount, which means there's no difference between them, which means the hydrogen can be added to either one, which means hydrogens can be added to both. Okay. When we run reactions, we aren't running a single molecule of each, we're running multiple molecules. Okay, so we get two products for that one. I'll try and go ahead and box it in so you can see, don't get confused by it. Two products for that. Okay, so when we move to the next one, okay, we might, particularly if you did these in sequence, go, oh, I've got an answer. And we could draw this guy, the starting material from our previous problem. Okay, why? Well, let's take a look at the product that we've got here, and that matches the products from the previous reaction. So that could be a valid answer, except if we go back to the previous problem, did we produce only one product? No, we had two. If I'd wanted two products, I would have given you two products, which means this cannot be the correct arrangement for that double bond. So we're going to have to come up with another way to do it, or another location to put that double bond. So when we looked at our our product, okay, we might have jumped on, well, first off, we should mark that bromine, okay, as being one of the reactive sites. And because we happen to have remembered that we had that other position, okay, I could have put a hydrogen at that position. We just said that that didn't work. Okay, well, what if I put the hydrogen over here? Does it make sense to do that one? Or for that matter, here or here? Why would those positions not really make any sense? Okay, hopefully what you can see is that they're not within double bond range of that carbon. Okay, which means those green ones don't make any sense to have attached the hydrogen to. Okay, so that really only leaves one position. We have to have run the reaction now between those two blue positions, which means if I go back to my starting material, where does the double bond have to be? Okay, it has to be at the very end. And when we go through, now we've got a way to check our work, go through and react this. Our hydrogen's going to go to the position that has the most hydrogens. So we could draw on our hydrogens. Where would we expect hydrogen to go? It's going to go to the end, which I'm now highlighting in red, to make a CH3. If we compare to our product, there it is. Okay? Where would the bromide go? It only goes to the next position. Okay? And we would expect this to be the sole product, because if we look at the other resonance structure on trying to put the hydrogen at the other position, say trying to add our hydrogen here, that would be a secondary anion, not as stable. Okay? Like I said, I am going through these kind of fast, so feel free to write down questions so when we get to lecture you can talk to me about it. So if we go up to the upper left one, we now want to go through and again evaluate what's going on with this. Whoops. Almost screwed up here. Let's go back to those last two problems we just did. Only the middle one. Okay. Through here. Okay, why would I want to address this one? Do we have a stereocenter? We do have stereocenters. Technically, we don't get just two products, we get four. We get a plus minus here and a plus minus here. Okay, because both of those generate stereocenters at what I'm now going to highlight as the blue carbon. Okay, that carbon is a stereocenter, which means I have to specify that chemistry. Okay. We don't have to worry about it for, we don't have to worry about it for that last one, because the answer that you needed to provide was the starting material, and the starting material doesn't have a stereocenter to be concerned about. Okay, so we don't have to worry about that one. When we go to the next problem, our upper right, okay, you'll notice that we actually start with stereochemistry. Okay, but is that a reactive site? No. We're only looking at alkane chemistry about that carbon. So while it's important to specify that stereochemistry in our product, that's not where our reaction is going to occur. Our reaction is going to occur at the solid red dots. So if we go through and draw out our product, we don't do anything to the ring. We don't do anything to our stereocenter on the other side. We don't do anything to that carbon. Our hydrogen would go to the blue position, because our blue position already starts with the most hydrogens. Okay, we'll make it bigger in the starting material. So that means the chlorine needs to then go to our red position. So we could then draw on the chlorine at that position. Okay. Anybody notice anything special about our product? It has a stereocenter now at that, what is soon to be that red position, which means we must specify that we get, I'll show you yet another format. We could say it's a racemic product, or again we could say that plus minus. Okay, so we should be specifying that as we go. If you don't specify stereochemistry with your products, and it's still the correct product, you're going to get most of the points. Okay, you're just missing one of these smaller aspects of it, so you will still lose some points, but you shouldn't lose a lot. Okay. Come on, shrink. What? So now to the more challenging ones. We need to go through and identify what things changed as we move from reactant to product here. Okay, so what happened? Well, I absolutely formed that OH bond. Okay, so somehow or another, I need to add OH as a reactant. Okay. So now the next question is, did anything else change? Okay, so if that's a reactive position, I could have looked at this, okay, at the next red, or I could have looked at the orange position, or I could look at the green position. Okay, did anything, where did those atoms start in the starting material? Well, we could say we got red, orange, and green. Did anything change about those atoms? Hopefully what you can see is that the green position, we added an extra hydrogen, which means in the course of running this reaction, I must have also added another hydrogen. Okay. This is not technically the answer, but this is the answer I want you to get to at this point. We're about to address this chemistry in a second. Okay? So, we move to the next problem. Again, same idea. Identify the differences. What are the differences that you should see? Hopefully you see the bromines, and you should also notice that there's nothing else that changed. Okay? So as far as the reagents that we have to add 2 bromines. Okay? You'll notice that we are not adding a hydrogen. So we should not be saying HBr, because if you write HBr, you assume we're adding the hydrogen. Okay? So what's a simpler way or an easier way to refer to Br? How about Br2? Again, we haven't seen that reagent yet. We'll look at it in just a little bit. Last one. Hopefully we see that the Br changed. Okay, any other big changes here? So we could again go through and look at all the individual positions, and you should note that we're adding a hydrogen to that position, so somehow or another we have to add HBr. This one is on here for a very particular reason. Okay, take a closer look at this problem. Let's ignore the product for the moment, so if you can, hold your hand over it, okay, hopefully over your work. If you react that starting material with this reagent, where would you expect the hydrogen to go? Okay, hopefully what you see is that the green carbon has a hydrogen and the red carbon does not have any, which means the hydrogen should go to the green position, giving us a different product. Okay, this is something you would see in more advanced chemistry. I'm not going to test you on this again. I just want you to look for these patterns. Find where the differences occur, identify what things must be added to force some kind of difference. For those of you that care, the extra reagent we would have to add is a peroxide or any R, so any organic containing compound, bound to an oxygen, bound to another oxygen, bound to another organic containing compound. Okay, the bond in between those 2 oxygens is incredibly weak and forces some new chemistry. That new chemistry is free radical chemistry. We, thankfully or not, don't have to worry about that this semester. Okay, so we're looking at free radical chemistry here. So again, why ask this question? I want you to look for the differences. Identify the main differences. I don't care if you're necessarily right or wrong with an answer. Get that difference identified and marked. You have to be finding those differences. Okay? I noticed that was a problem for several of you with the previous exam, trying to find the reactants. Okay? So look for those differences, see what's going on with them. I do expect you to be able to find those differences and pieces. Okay? So that should have been a bit of a challenge to go through most of those. Should also give you plenty of practice to go through and work with. Hopefully those won't be too bad if you see them again on, say, an exam, maybe like exam 3 or something like that. Okay? So let's get back to the 2 new ones. Water and the bromine. So let's take a look at the water reaction first. Okay, so what we did was what's shown here. So in the process of doing this reaction, if we went through and kind of identified our pieces here, we're going to do the addition of water to the double bond. Our hydrogen, which is partially positive. Why is it partially positive? Good, it's connected to a partially negative oxygen. Okay, that positive hydrogen reacts with the double bond and gets added to, since I've got colors, let's go ahead and stick with them, to our red position. And we could add that hydrogen, and just for the sake of clarity, let's show the old hydrogen that was also already there. And then the OH would then go to our green position on our double bond. Okay? Hopefully you guys can see that. Very similar chemistry to what we saw with our acid-base chemistry. Okay? With the alkene reacting with HCl and HBr. Okay? So you'll notice also I'm bringing up the not probably politically correct face test with this. When we reacted the alkene with HCl or HBr, one of the first things that I asked you was pulling a face test. Okay, which would you rather have splashed in your face? HCl, which you know is going to hurt, or an alkene, which we don't really know anything about, so it could very well not hurt us. Okay, well, HCl is going to be the problem. So we focused our chemistry on the HCl. Okay, so if we pull that same face test argument with the alkene and water, okay, splash alkene and water in your face. Water, in theory, you splash in your face every day, okay, isn't going to be a problem. The alkene, we don't really know anything about, okay. If we go back and evaluate overall reactivity, what are the bonds in an alkene? We have carbon and carbon and hydrogen. All of those are covalent. There's no real polarity associated with them. So if we were just going to take a stab in the dark as far as how reactive our alkene is, we'd probably guess pretty low in reactivity. Okay, that's where we run into a problem. We're trying to react two things of very low reactivity. Okay, so to get water to react with the alkene, we have to add something else to get the reaction going. Okay, I don't remember if that's on this slide or not, so let's go ahead and click ahead. Nope, it's not, so let's go back and fix it. So when we looked at HCl and HBr, okay, those additions, to get the chloride and the bromide on, I had to have a positive hydrogen, okay, a really positive hydrogen. Okay, so when we look at HCl and HBr, I know when I drew it out, I showed that bond. But what do we know about HCl and HBr? They're both strong acids. They both completely dissociate in water. So when we look at the reactivity, we're really not looking so much at hydrogen starting with a bond. It's coming off as H+. When we go back and look at water, okay, let me take a step back, go back to our acid-base one. So we know it completely dissociates, so how would we classify the bond between hydrogen and chlorine, now shown in red? Okay, well, if it completely dissociates into the ions, we might expect that red bond to be ionic. Okay, so as far as bond strength goes, relatively weak. When we move up to our water molecule, and we now look at the bond between the hydrogen and the oxygen, okay, it's not ionic, it's polar covalent. Okay, polar covalent is a relatively stronger bond than an ionic bond. What does that mean? That means the hydrogen in water is not very positive, which means it's not reactive enough to react with the double bond. So that if this was all I put into the reaction, just the alkene and just water, what would I expect for a product? No reaction. That looks really terrible. Let me try that again. Sorry. No reaction. Okay. So if I am going to get a reaction, I have to force the alkene to react. Okay. Well, how did the alkene react when we reacted with HCl and HBr? Reacted as a base. Okay, so maybe what I should add would be an acid. So instead of adding just water, let's add, for instance, HCl. Okay, let's see what happens in this case. So when I add HCl, my alkene is going to react with the acid. It'll share its electrons with that hydrogen. We break that bond. Okay, and what do we generate for our product? Okay, hopefully you can draw this out faster than me. We'd get our old hydrogen that was on there, our new hydrogen that was on there, and then we also have that carbocation. Okay. So I know in almost all cases you always heard me say, I only care about the organic, I only care about the organic, I only care about the organic. I'm apparently wrong. Okay, so what we're going to do is the other part of this that I need to care about is now the nucleophile. I've got water. Water can act as a nucleophile because it has that lone pair. And then I've got chloride. Both of these are floating around in solution right now. Okay, which of those is the stronger nucleophile? Well, what is a nucleophile? It's an electron donor. First thing that we should look for with an electron donor is donatable electrons. Oxygen, chloride, okay, both of those are donatable. Negative charge is a really big red flag. And typically when you see negative charge, you should be thinking that is a strong nucleophile. So when I compare chloride to water, which one's my strong nucleophile? Chloride. So what would the product be if I mixed all these three things together? Well, my product ends up being chloride. The chloride addition, not the water addition. Well, crap. Okay, this reaction has to work. Okay, well, it doesn't have to work, but I'm telling you it works. So something else has to be going on here. Chloride is a bad choice, so I can't use HCl. Okay, so we need to pick a different acid. Okay, and the acid that we pick has to still supply hydrogens. Why not? No, let's go blue. Okay, but the hydrogen that it supplies, or the conjugate base of this acid, must be non-nucleophilic. Okay, I know there's a lot of words in there, easy to get confused. A non-nucleophilic acid. Have we mentioned any of those yet this semester? Okay, hopefully you remember that yes, we did. We could use this acid, sulfuric acid. Okay, so now when I go through and evaluate the products at the intermediate stage, okay, I still have water, and now I have sulfate. Okay, except sulfate's still negatively charged. Ooh, dangerous. We still see that negative charge. But why is this negative charge non-nucleophilic? Okay, everybody's favorite 7-letter word. We'll test that guess in a second here. What can I do with sulfate? I can move the electrons into the structure, and I can do 1, 2, 3, 4, 5, 6. Well, here, let's make sure that's all 7 letters. What do we have? We have 3, 4, 5, 6. Resonance. See, all one word there, one letter there. So there we go, 7 letters. 3, 4, 5, 6, 7 letters, because it's resonance, and the NCE counts as 1 letter. So we've got resonance. What does that resonance do to that negative charge? Stabilizes the negative charge to the point where it's no longer reactive as a nucleophile, which means water can now react, okay, and we can move forward with our mechanism. Okay, you notice I'm saying forward with the mechanism and not making the product. Okay, why not? Well, let's look at the, well, I think this is going to be a big mess in here, so I'm going to erase all this. Let's go ahead and see what the product is of this next step. Okay, water reacts with our carbocation. Okay, I'm going to start implying those hydrogens now because it's no longer relevant to our mechanism. We've got the bond. Go ahead and show that in red so it stands out. And just as a reminder, our arrow shows the flow of electrons, so we're taking the lone pair of electrons on that oxygen, one of those lone pairs, and we're sharing it with the carbocation. Okay, and we've got that oxygen now at the end of this that was supposed to draw. Let's go ahead and show the other bonds that oxygen has. It's got the lone pair. what's going on with that oxygen now? Started neutral, lost electrons, it's now positively charged. Okay, so our structure is not stable. That oxygen does not want to be positive. So what it's going to do is steal electrons from its easiest source. Where's the easiest source? Probably going to be from the carbon, actually, which means we're looking at a reversible reaction. But let's go ahead and be, optimists and say we can get it from another source. That other source being our hydrogen atoms. So we can take the electrons from the bond between the hydrogen and the oxygen, and we'll put that on the oxygen. What does that end up giving us? Well, turn the corner, and there we go. We've got our final product plus H+. Okay. What pulls off that water molecule? Okay. The hydrogen atom. This isn't something that I'm particularly concerned that you know, because it's kind of a dicey question. What I would specify is that we've got any kind of base that's present, and base in this case is, we could almost put in quotes here. We're not strictly adding a base, because if we add a base, what happens to sulfuric acid? We don't have any sulfuric acid. So we're adding, it's anything that has electrons that can act basic. So we've got other water molecules in there. We've got other now alcohol products that can pull off the hydrogen. We've got the sulfate anion that can pull off the electrons. Okay. So don't get bogged down in the specifics of what that base is, or even that last blue mechanistic arrow. Okay. I'm not concerned about that at all. If it's something that bothers you, I can absolutely walk you through a couple examples to really kind of put that in there, and you can continue to show it. Just don't show it wrong. Okay. So one last thing I want to do before we continue on to the bromine is go ahead and finish off with the last piece or last thing that's left in our reaction. We still have that sulfate anion. We've got a negative and positive there. If we really wanted to balance this out, we could put those together and we get H2SO4. Okay, so one of our products is H2SO4, and one of our reactants was H2SO4. What does that mean? What's the role of sulfuric acid in this reaction? Sulfuric acid acts as a catalyst. Okay, so the addition of water, okay, must be acid catalyzed. Okay, so it's one of the big repercussions of this reaction. Catalyzed. Okay, must be. That acid catalyst needs to be something non-nucleophilic. Sulfuric acid happens to be a really good non-nucleophilic base, so I guess I can add that next to it. Okay, so we're looking at non-nucleophilic. Okay, so I know a lot of arrows floating through there. Hopefully you can piece that together. If you want me to in class on Monday, I can just show the mechanism and simplify it now and just show it up on the board. Okay. So that's how we'll get water added to a double bond. Interesting thing that we can add to this, in the process of doing this, we've now added a new functional group. Okay, we have an OH attached to an alkane. So what we've got is an alcohol. Okay, so the addition of water to an alkene generates alcohol products, hence we'll talk about alcohols after this chapter. Okay. We're talking about it now because it follows very similar chemistry to the HCl and HBr additions. Okay. So now what we're going to do is move into some other chemistry with alkenes that doesn't or isn't, in my opinion, as obvious, if you will. None of it is super obvious, but I think this stuff's a little bit easier to see. Okay. I'm pretty sure we've already seen this in lab, this particular reaction, alkenes with bromine, or the addition of bromine to an alkene. I'm not positive. We might be seeing it in Monday night's lab. Okay, so what is happening in this reaction? Okay, if we try to pull a face test argument with this, we get bromine and alkene. Well, bromine's neutral. We're looking at a covalent bond because bromine isn't more electronegative than bromine. And we're looking at a covalent bond in the alkene. We don't really get any difference. Okay, so what we have to base the argument on for this is that our alkene is a source of electrons. Okay, so we don't get the extra benefit of having an acid to react with. We're going to have to say that the alkene supplies electrons. So if I'm going to look at a mechanism for this, the alkene's going to share its electrons. There's only one place that it can share them, so we're going to have to move it towards that bromine. Okay, we just don't have any choice in this case. And we'll talk about a couple reasons why we're allowed to do this once we get the basic mechanism down. Okay, how many bonds would that bromine then have? Okay, well, we get 2. So again, we need to break a bond because bromine, as far as we're concerned in organic chemistry, can only have 1 bond. So we end up breaking that bond, and we get kind of an intermediate from this. Okay, so let's go through, and I'm going to draw an intermediate product off on the side here. It's going to be a bit irritating because it's not technically part of the mechanism. Okay, and let's go ahead and put the bromine, let's say, here. Okay, which would mean we got those electrons around it, and we would have a positive charge here. Okay, that positive charge is incredibly unstable. And previous reactions, we had a nucleophile come in and react with it and ultimately stabilize it. The reason we had to use a nucleophile to stabilize it is because there wasn't a closer source of electrons. Okay, so this is where it gets a little bit weird with this. Is there another source of electrons? Okay, nucleophile is found outside the reaction. Is there another source of electrons found within the reaction? Okay, say with a whole bunch of lone pair electrons around it. Okay, we've got the bromine that's actually found within the structure. Because it's so large, when it reacts with the double bond, it kind of inserts itself in between those 2 p orbitals. So in one case, it's got electrons coming from, we'll go ahead and call it our red carbon. But in the other case, it's sharing its electrons with our blue carbon. Okay, so instead of getting what I've got drawn as a pseudo-transition state, what we end up getting is this ugly beast of a thing here. We get this structure. Okay, the bromine ends up becoming positive because although it accepted electrons, it also shared electrons. Okay, so it becomes positively charged. This intermediate is known as the bromonium cation. Bromonium, I think. Cation. It's incredibly important for this overall mechanism, and we'll talk about how we know this species actually exists, and we're not moving through the carbocation that we would have over here. Okay, and we'll address that in just a second. Okay. At this point, we've got that positive bromine. We still have bromide floating around in solution. Okay. Does our bromine want to be positive? Nope. So what it's going to want to do is steal electrons from one of those carbons. Okay, so when we go through and look at those 2 carbons, is one of them more susceptible to a loss of electrons? Said another way, does one of those generate a more stable cation? Okay. No. Well, that means neither one it doesn't really matter which one we decide to react with. So let's go ahead and pick, I'm going to pick this one over, well, I'll pick this one over here. Okay, so those electrons are going to push towards the bromine, okay, or our bromonium cation. But then we end up starting to form that positively charged carbocation again. We said that doesn't happen. So we need something to cause that bromine to get kicked out of there. Something must force it out. So we can have our other bromide come in and force that bond to break. Okay. And I'm going to draw it again, even though I know the answer is already shown there, but I'm going to draw it again. Okay, and it's going to look messy, but that's okay. We've got our bromide, okay, there, and we've got our other bromide over here. Okay, because I got colors, let's go ahead, overlay here. We've got our green bromine, and blue bromine, and blue bromine. Okay, so those two bromines end up getting added to the structure, and you should be able to see that we can equate what I've got drawn and that final product. Those are, this, for all intents and purposes, the exact same thing. The only real difference is a rotation about the sigma bonds. Okay. So why did I draw it out like this? Okay, when we go back to the bromonium cation, we have effectively a cyclopropyl ring. Okay, the carbons in that cyclopropyl type ring, so I will flag those as red. What's the hybridization of those carbons? They're sp3. Okay, why is that important? Well, we've got a nucleophile coming in and kicking out a leaving group around an sp3 carbon atom. That sounds pretty familiar. That kind of sounds like an SN2 reaction. And what we're doing is a backside attack on this SN2 reaction. That means that this bromide, our green bromide, comes in from the backside of that leaving group leaving. Okay, so well, what does that mean? So let's go through and say, add some kind of stereochemistry to this so we can see it a little bit better. Let's say that that bond was wedged right here. Okay, well, if that one's wedged, what did the bromide, our green bromide, come in and do? Where would it be if we looked at our product? Okay, hopefully you should be saying that it would be dashed. It's coming in from the back side. Okay, so that's kind of neat. We're sort of adding some stereochemistry to this. It's not technically stereochemistry yet-ish, but we're addressing the dynamics of this mechanism. Okay, if we go back to our bromonium cation and that blue bromine, if we specify one of those bonds as a wedge, what must the other bromine carbon be? Okay, so if we're trying to build a cyclopropane, so we're looking at a three-membered ring, okay, so you could do the whole diamonds in the sky kind of thing, right? I guess it's triangles in the sky, close enough. Is it possible that I could have a cyclopropane ring, so try and hold your hands together in that triangle shape, and aim that triangle towards you? Okay, can I have any one of those bonds, okay, be going away, or for that matter, in the plane, okay, and still have a complete cyclopropane ring? Hopefully what you should see is that as you try and do that, you must break contact between your fingers, which means you're no longer forming a bond. So if I say one of those bonds is wedged, what is the other one? The other one must also be wedged. Why is this important? Well, let's translate that information back over to our final product, and we get a wedged bromine. Go through all that trouble And now comes up with an interesting question. How would you describe the relationship between our blue and our green bromines? Are they on the same side of that alkane or that single bond, or on opposite sides? Opposite sides. So what we're looking at is a trans product. Okay? And it's a bit odd to say in this case, so we'll put trans in quotes. Why is it odd to say? Well, this is all sigma bonds, and we can rotate those sigma bonds. So saying trans here is a bit odd. But if our starting material was put in a position where we can't do a rotation, we end up with a trans alignment of those bromines. One must be coming at you, one must be going away. Okay. Also, one of the repercussions of this particular reaction is that we have no way of deciding where that bromine comes in and reacts from. We do end up with a racemic mixture, so we could go through and say the plus minus again. Okay. So we've looked at a generic mechanism here, so let's go ahead and move to the next slide, which shows this a little bit better. Okay, at least I think it shows it a little bit better because I drew it out. Okay. This type of reaction works with both bromine and chlorine. Okay. And it's really driven by the fact that we're dealing with these halogens that are really, really, really large. Okay, which means their electron clouds are kind of massive, which is why when that bromine comes in, so if I attempted to show the double bond, okay, and we'll pretend we can see the cycloalkene behind it, but if we had the double bond, okay, with our p orbitals, is that bromine atom kind of just sits in there. Okay, so it can share electrons and accept electrons all at once, and because it's so big, it interacts with both lobes of that p orbital really, really well. Okay, so that single atom is approximately equal bond distance in between those. Okay, which is why we can get that cyclopropyl structure. Okay. And that's one of the reasons why the bromine atom can stabilize the carbocation, and we don't see a carbocation intermediate. So it's a bit bad to call it an intermediate, but it facilitates stabilizing what we would have predicted to be the carbocation. Okay, and we know we don't form the carbocation because if we did, and we looked at our final products, we would expect a mixture of some bromines being wedged, some being all wedged, all dashed, one wedged, one dashed. We would expect a mixture of all of those options. And the only mixtures that we get are with one bromine dashed, one bromine wedged, every single time. Which means we must have an alignment such that the other bromide, or that the bromide comes in and attacks from the backside. Okay? It has to come in and attack from that backside. Okay, we don't have a choice, which is why we see that trans product. Okay, so when we're looking at the addition of bromine, we're looking at a trans product, wedges and dashes, and it's all because of that bromonium cation. Okay. We'll come back to some extra terms when we summarize our alkene chemistry a little bit later on. Okay. Starting to push time here, so let's see what I've got next. I think I've got one more reaction I can get through. Yeah, let me check one more. Yeah, let's go ahead and just finish it off with the reaction with hydrogen. Okay, very, very similar reaction to the halogens, sort of. Hydrogen is much, much smaller than bromine or chlorine, and because of that, we can't just add hydrogen straight to a double bond. We're going to have to add something else in there. Remember when we looked at the bromonium, oh, I erased it. When we looked at the reaction with our bromine, we said the bromine was large enough that it could sit in between the p orbitals, okay, and interact with both, helping us to form kind of that cyclopropyl type structure. Hydrogen's so small, and it doesn't have enough electrons to really allow for that intermediate. Okay, so what we have to do is add a catalyst to facilitate this reaction. Okay, so I think this diagram does a relatively good job of showing how this catalyst works. So when we're doing the addition of hydrogen to an alkene, what's going to happen is we'll add a metal catalyst, typically platinum, palladium, nickel. I mean, there's tons of different options, but some kind of metal catalyst. Hydrogen will be bubbled into the reaction. That hydrogen sort of sticks to the metal surface. The alkene then comes through, okay, and also sticks to the metal surface, and we end up getting kind of an intermediate where they're sitting next to each other. Okay, the alkene and the hydrogen molecule float around or shift around on that surface until we get them very, very, very close to each other. Okay, and then what ends up happening is the metal facilitates the transfer of electrons from the pi bond. Okay, so we take the electrons in our pi bond, goes into the metal, and then out to our hydrogen. Okay, and that allows us to then add our hydrogen to one side of the double bond. Okay, at this point, the other carbon is now missing electrons and is incredibly unhappy about it, except for the fact that the metal is saying, hey, you know what, dude, I'll help you out. Okay, so the metal's providing some electrons to that carbon to help kind of keep it happy. Meanwhile, we also still have some electrons from the other hydrogen, which is now also not particularly happy. So what ends up happening is the metal facilitates the transfer of the electrons from that hydrogen over to the carbon, and we get the removal, or then the final kickoff, of our alkane product. So if we look at an overall reaction, we're starting with a carbon-carbon double bond, in this case CH2CH2. We add hydrogen over typically palladium, and we get CH3 in this case. Okay, so it's just the addition of hydrogen to the double bond. Ultimately the same kind of thing as that we see with the bromine or the chlorine. We just have to have this metal catalyst that facilitates this. One of the big differences here between this and our bromine, if we look at our final product down there, those red hydrogens, what's the relationship between them? They're on the same side of the structure. When we look at our product formation, we get the cis addition, okay, of our hydrogens. They're added to the same side of the double bond. When we go back and look at the bromine reaction, okay, they're added on opposite sides of the double bond. We get a trans product. Okay. I will talk about anti and technically syn on Monday. We'll kind of finish up the rest of this, and we'll work on the quiz based on all alkene chemistry. Okay, so make sure you write down some questions for me. If everything's good, great. No one showed up to office hours, so I'm going to assume you all love easy nomenclature and find it easy. In any case, I will leave you with that bad joke and talk to you on Monday. Have a good rest of the week.